and good evening. So today we are discussing about lab 4, which is transmission line, no load and matching impedance. So okay, this is our members as usual. Okay, first the learning outcome. So based on the report that we did for these experiments, at the end of this lab session, students should be able to identify the characteristic parameters of line operation under no load during matching and during symmetry. Okay, so the second one is the equipment and the component that we use to do these experiments. Okay, so the equipment and components that we use is first transmission line model 150 km and 300 km. And second one is power switch module. And third, resistive load 3-phase 1 kW and inductive load 3-phase 1 kW and capacitive load 3-phase 1 kW. Okay, for the third one is we are going to discuss about the synopsis and theory, also for the procedure. Okay, so the figure 1 experiments, the circuit for measurement in no load, matching and short circuit mode. So these are the experiment that we need to be complete, and then the procedure that we have to follow the instruction given. Okay, so next one is experiment procedure based on the diagram given above just now. So for this one, we set up the no load circuit as illustrated in figure 1 just now. This one. Okay. So first, we disconnect disconnect the resistive load to study operating response under no load. And then second one is for the line length, set the voltage to the nominal value 380 volt at the beginning of the line. So the conductor are designed L1, L2, L3, and then the neutral conductor N. So measure the variables, indicate the table. So we are going to show the table after this. Okay, so this is the table for the line start and then for the line end. This table is for line length of 100 km voltage, yes. And then this table 2 is for the line length of 300 km for the line start and then the line end. Okay, for the calculation is to determine the voltage rise at the line's open end, and it is the best to use the voltage measure that are to calculate the voltage at the line start. Okay, so this is the calculation that we did for this table that we got the data inside the table. So for the line length of 100 km, and then we use I20 U2 times with omega C and then divided by 2, so we got the answer 0.04 ampere. And then while the UL we got 2.53 volts, and then U1 is we got 220 and 220.5 voltage. And then for the line length of 300 km, as usual we got 0.145 ampere. For the UL we got 10.48 voltage, and then for the U1 we got 220.5 volt. Alright, so in this case QC is equal to 3 time with UN divided by square root 3 and then square it and then time the omega and then time with C. So the answer for the line length of 100 km, for the QC we got 90.7 var. And then for the line length of 300 km, for the QC we got 181.4 VAR. Sorry. Okay, for the draw electrical schematic diagram by consider safety condition, labeling the components and the sending and receiving end section. Okay. So for the 100 kilometer, this is the schematic diagram for transmission line model 150 kilometer. Alright, so this is the inductive load, this is the capacitive load, and then the resistive load. So this is the L1, L2, L3, and then this is the ground going down, and then this one L1 going here. Every box of the load, like capacitive, inductive, resistive. Yes. Okay, so for the second schematic diagram, so this is for the transmission line model 300 kilometer, as the same diagram as before. So this is the inductive load, capacitive load, and resistive load. So this is the ground, and then this is the power supply, and yeah. Okay, based on the data we got from the experiment for the table 1 and table 2. So here are the questions that based on report. So why do the result of the line voltage at sending and receiving a little bit different in case 150 km, but obviously different in the case of 300 km? So here are our answer. First, the reactive power is negative, and then the load is leading power factor load, and then for the leading power factor load, the voltage regulation is negative, and then for the receiving end voltage will be more than the sending end voltage. Okay, second question. Compare the measurement result with the calculated values that make you summarize based on comparative analysis. Okay, first we can say that voltage dropped more in second table on 300 kilometer line, and current also more in 300 kilometer line. And then second, we can say that the active power is 0 in 100 kilometer and very less equal with 1 watt. So the third one is the reactive power requirement is higher in 300 kilometer line than 150 and then the 150 kilometer line. Okay, for the matching under load, this one we need to study the response during the matching. The resistive load is decreased from its maximum value, and then this case is for both line length. The nominal voltage 380 volt is to be set at the start of the line and maintain this value through readjustment wherever necessary. So the variables indicate next are to be measured. So here are the results. Okay, the result for the line length of 150 kilometer, the power watt, the voltage L1, L2 that we've got, the current, the active power, and then the active power as usual. And then this one is for the line length of 300 kilometer that we got the results from the experiments, as well as the previous result is the same, but it's a different a little bit. Okay, so we can say that is situated between this range in the operating state known matching. The supplied reactive power is now at its minimum value, which is theoretically the value is 0. So this operating point is to be found by slowly changing the load resistance starting from its maximum value. And then for the third one, we can say that the measurement values during matching, the line of 100 kilometer and supply voltage of 300 volt. Okay, for the table 5, the result for the line length of 100 kilometer and supply voltage 380 volt. Okay, so this one is for the result for table 5. So the active power is 555, and then the voltage L1 minus L2 for the voltage L1, L2 is 368, and then the current, the active power, and reactive power as well. And then the table 6, this one is the result for line length of 300 kilometer and supply voltage 380 volt. So the active power of the load, natural power in this case in watt. So this one is the result is 547, while this one we got 555. So it's a little bit different, slightly different. It's not in big gap of difference, the result that we got. And then as well as the voltage, the current, the active power, and then the reactive power. Okay, the equation for power is U square divided by R, which is R equal with U square divided by P. So it's used to calculate the responding load resistance, which also represent the characteristic impedance, okay, which is the line-to-line voltage across the load. Okay, and for the R value for line length of 100 km, we got 244 ohm. And then for the line 300 km, for the R value is 245 ohm. R means resistant load that we got. Okay. So this one is the schematic diagram for. So this one is for the schematic diagram. Consider the safety condition, labeling, and components, and only at the receiving end section. Okay, this one is for the transmission line model for 150 km. As well, it's the same schematic diagram as before. So this one is the power supply, this one is the inductive load, the capacitive load, and resistive load. So this one is the ground going down, and then this one L1, L2, L3, and neutral line. Okay, this one is for the transmission line model for 300 km, as same as before as well. It's no different, just slightly different. The slightly different in data. Okay, my friend will explain more based on the data tabulated for the next experiment. Thank you.
I will continue to my part, which is data tabulated based on table 3 and table 4. So here we have made a discussion that for the feature of the result based on this argument. So what can you suggest? Result in medium transmission line for 150 km and long transmission line 300 km. So the first one is the Ferranti effect observed in the long transmission line is more. Second one is at low load, the receiving end voltage is higher. Third one is at higher load, the drop in voltage at the receiving end is observed more in long transmission line. The fourth is voltage regulation is poor in long transmission line compared to medium. Next. So, compare the measure result in medium transmission line and long transmission line. The Ferranti effect is more dominant in long transmission line. As load increase, the reactive power drawn by the line increases, reactive power generated by the line. The rating of shunt capacitors and reactors to be used for long transmission line will be higher than medium transmission line. And long transmission line, the line inductance to be decreased by increasing the GMD, which is geometrical means of distance of the conductor. So the voltage drop in the line, the reactive power drawn by the line decrease at higher loads. So what is the relationship of those result in table 5 and 6? So when the length increased from 150 km to 300 km, the impedance also increased. From the formula of P equal to V squared over R, we know that when the value of resistance increase, the value of power will decrease. The table also show the result for 150 km by 555 watt and 300 km by 547 watt that we have calculated before. So compare the measurement result in medium transmission line and long transmission line. So when the length increase from 150 kilometer to 300 kilometer, the voltage and active power will be decreased, but the reactive power will increase and the current value will remain constant. So I will proceed next slide to Azizi Aiman. Thank you.
Okay, for the conclusion, finally the parameters of a line running under the no load during the matching and when symmetric may be identified. To study the operational reaction, we disconnect the resistive load in the no load circuit. At the start of the line, we set the voltage to the nominal value 380 volt and the outside conductors are labeled L1, L2 and L3 while the neutral wire is labeled N. The resistive load is reduced from its maximum value until the power level specified are attained to obtain the response during matching under load. The nominal voltage 380 volt must be established at the beginning of both line lengths. 150 km transmission line, medium transmission line, and 300 km transmission line, long transmission line, and maintained by change as need. Between these two range is the operational situation known as matching. The amount of reactive power available has now dropped to its lowest point theoretically zero by gradually increasing the load resistance from its maximum value. This operating point can be found. That's okay. Next question. Why at receiving end of transmission line current at power P active power, Q reactive power, S apparent power is zero? Okay, for the first point, Faraday effect happen on an energized long transmission line more than 80 km. Second one, which may cause the voltage increase in the receiving end of an electrical transmission line when it's operated in a no load or low load, which define I receiving equal to zero in no load condition. The third one is this effect occur as capacitance and inductance are the main parameters of the lines and due to the charging current of the line. Okay, that's all from our group. Thank you.
Okay, thank you.